In this video we're going to be discussing about dielectrics. Okay, now it's on the board, and then there are a series of diagrams that will help us back up the explanations to the equations and formulas we'll be talking about and deriving as well. Okay, now it is quite an easy concept, and all you have to do to understand this concept is follow every bit or every step I take in explaining this series of diagrams we're having on the board. Now, first things first, what is a dielectric? Now, we do know that for a capacitor, there's usually a separation between the plate, the positive and the negative plates. To the left, we have the positive, and to the right, we have the negative for this series of diagrams we're having here. Now, the space in between is where we put the dielectric. Now, the dielectric is an insulating or non-conducting material. Okay. Now, what it does is that it helps us to induce charge. It does a whole lot of things. Okay, but basically, it induces charge and helps to separate the two plates from touching each other in a capacitor. Okay, the dielectric could be made of ceramics, paper, or mica. Okay, provided it is a non-conducting or an insulating material. Now, what we'll notice is that for a capacitor that is having no dielectric, you notice these parts that are curved simply means there is not a material in between. But for this one, there is no material in between, it's just free space or air. Okay, now for a material like this, having a surface charge density on the left hand side, which is positive, and negative charge density on the right hand side. Okay, still on the four diagrams, what we'll notice is that for a potential difference of V naught, for example, okay, let's say it's having an initial potential difference of V naught, the charge on it is given as C times V naught. Okay, or we can even say the initial charge. Now, this is a formula that we've talked about in the case of capacitors. Okay, we talked about this formula. I will prove this when we explain capacitors. So if you don't know how we got to this formula, you can as well watch our videos still on the playlist on capacitors. Okay, and then you get this one straight. Okay, now Q naught is equal to C times V naught. Of course, C is a constant, that is the capacitance of the capacitor, which depends on these two values. Okay, so as both of them are increasing, we can also get a fixed value for C. Both of them decreases, to get a fixed value of what? C as well, because they both increase or decrease simultaneously. Now, after we introduce a dielectric, what the dielectric does is that it now brings in its own charge. Okay, it brings in its own charge, which now distorts the electric field we are having here. Now, on this next diagram, we've now brought in the dielectric. Here is the material. We'll put the material inside. Okay, we put the material between the plates to separate it. What it does is that it induces its own charge. You can see it in the diagram C. Now, in diagram C, initially we were not having a positive or a negative charge at the side of the plate, but now we're not having positive, negative on the opposite side. Okay, the positive charges will now go to the negative plate, and the negative charges will go to the positive plate. That is exactly what we're having here. Okay, and then you notice that the electric field here, they are now being what now? Reversed. Some of them, initially all the electric field were moving from positive to the right, which is by default, right? Now, after putting in the dielectric, some of the electric fields will not be reversed due to the charges that are being what now? Induced. Since they are being reversed, you notice that they are vectors. Okay, some of them are going to cancel as the one going to the right along the line. Okay, after they've cancelled that, we're not going to be left with a new system, which we are seeing in option D. Okay, we're going to be left with a new system like this. In this case, the electric field that are cancelled as, they are going to disappear. That is why you are seeing that the electric field has now reduced. So it is important to notice that when a dielectric is fixed into a capacitor or a material to parallel plates, what happens is that the number of charges is going to increase, of which you just explained. The dielectric will bring its own charge, it will induce it. Now, the number of charge is going to increase, but the electric field is going to what now? Decrease. We're still going to come to that, okay? But it is important to take note of it, that the number of charges are going to increase, and then the net electric field is going to what now? Reduce. Now, we already said this is an important equation to take note of. I'm going to call it equation 1. Now, let's see the explanations to the other formulas that will be derived for these concepts you're having on the board. Okay? Now, first things first, when the dielectric is being introduced, it brings in its own charges, right? That is important to take note of. What we notice that the various values or quantities like charge, potential difference, electric field, they tend to start changing by a constant value, by a particular value. Now, they start changing by a particular value, which we've talked about in our previous video. permittivity of free space or relative permittivity of the medium or permittivity of the medium. Okay, now in this case we're going to be dealing with permittivity of the relative medium or relative permittivity of the medium, that is epsilon with a subscript of r. Okay, now this is called the relative permittivity of the medium. Okay, they tend to increase or decrease by this constant value. Okay, some textbooks you find it written as k, but I don't want to replace it as k because you might be thinking it is the value we're having in Coulomb's law, which is k equals 1 over 4 pi naught. So I'm not going to replace it as k. Just telling that some textbooks you might find it as k or some materials as well. Now, relative permittivity of the medium. It is this value that will help change the number of charges, the number of electric fields or potential difference that we are having. Okay, now what we'll notice is that the potential difference tends to decrease after we've added this dielectric. That is what happens. The potential difference tends to decrease, and the potential difference decreases by this particular constant or this particular element. Hence, if we're having an initial potential difference V naught, the new potential difference V is now equal to V naught divided by the relative permittivity, okay, epsilon R. Okay, so this is what we're going to have. Now I'm going to call this equation 2. Now, how about the capacitance of a capacitor? What you notice is that immediately we add this dielectric into the system, the capacitance become increased by this value as well, okay, relative permittivity. So if we're having an initial capacitance C naught for a capacitor, after introducing a dielectric, what happens is that the new capacitance is now increased by the value. So we're going to have relative permittivity times the what now? Initial capacitance. So I'm going to call this what now? Equation 3. That is also important to take note of the general formula for relative permittivity. So I'm going to write it here and call it equation 4. Okay, I'm going to say relative permittivity, of which we know is the permittivity of the medium divided by the permittivity of free space. Okay, that is another useful equation. Now I'm going to come here and take the other ones. How about the electric field and the charge as well? And how about the energy density? Now, if you recall, we did derive in our other video on energy stored in a capacitor that the energy density is given as 1 over 2 permittivity of the medium times electric field intensity squared. Okay, that was what we said. We said the energy density, that is energy stored per volume, is equal to half times the permittivity of the medium, okay, times the electric field intensity squared. Now, if we try to introduce in a dielectric to increase the capacitance, the energy is also going to change, and the energy then becomes U is equal to 1 over 2 relative permittivity times permittivity of free space epsilon squared. This is what we're going to get. Okay, so I'm going to call this equation 5. Okay, now what then happens to the electric field? Remember we said that after adding the dielectric, what happens is that charges are being what now? Induced, right? So we do know that the number of charges are going to increase. Now, how about the electric field? Initially, look at the amount of electric field you had. 1, 2, 3, 4, 5, 6, 7. And then when you come here and count 1, 2, 3, 4, 5, you see it's now less. So notice that the number of electric field that we'll now have in the end after adding the dielectric is now what now? Less than the initial one. So we know the electric field is what now? Decreasing, or it's decreased. Now, how do we know the amounts by which it decreases? Still depending on this value, okay? So we can now notice that, or we can now conclude that the new electric field is also going to be equal to the initial electric field divided by the relative permittivity. Let's call this equation 6. Okay? So it also what now? Reduces by ER or epsilon R, okay? So the net electric field or the new electric field intensity is now equal to the initial one divided by subscript of R. How about the charge? Now, if we assume the potential difference to be constant, or we could say that since we have added the dielectric, we do know that it will induce charge on it, right? More charges. So it means that the new net charge will now be equal to relative permittivity times the initial charge. Remember, this one is increasing, not decreasing. That is why we are multiplying. So I'm going to call this equation 7. Okay, now it is also important to take note of the induced charge. Now, if we're having a system like this, in this case, we're not having any net electric field, right? Or rather, we could say the net electric field here is E naught. So if the electric field at this first case is E naught, and then we bring in this dielectric, and the dielectric induces charges, which then induce an electric field that opposes the initial one, right? So it is bringing in electric field intensity, which I'm going to call the induced charge. The reason I'm subtracting is because it is decreasing it, because in the end, we do not have few number of what now? Electric lines. Okay. Now, this is equal to the net electric charge that we're going to get, right? So I can also come here and I'll say the net electric charge, okay, after adding the dielectric will be equal to the initial electric charge, or rather electric field intensity. So the net electric field is equal to the initial electric field intensity minus the induced electric field intensity. Okay, so E is equal to E naught minus the induced electric field intensity. Now, if you recall, we already talked about E. Okay, we said that E is equal to E naught divided by ER. So I'm going to replace it with E naught divided by epsilon R, and this is equal to E naught minus EIND. Now, I can choose to make the induced electric field the subject. If I do that, I'm going to get the induced electric field is going to be equal to E naught minus E naught divided by relative permittivity. Okay, now if we continue with that, we're going to get the induced electric field intensity is going to equal the initial electric field intensity in brackets 1 minus 1 over relative permittivity. Let's call this equation 8. So we can now see that there is a new formula for calculating or solving for the induced electric field intensity after the dielectric has been added to the system. Okay, now we can as well play with this formula a little bit to manipulate. So get the induced charge. Okay, we can manipulate this formula to get the induced charge. Now we do know that from Gauss law, okay, the electric flux is equal to electric field intensity times area is equal to what now? Charge divided by permittivity of the medium, or relative permittivity rather. If I divide both sides by A, I'm going to get E is equal to Q divided by A is the charge density. So I have the charge density divided by permittivity of free space, right? Now, also we could say that induced charge density is equal to, induced electric field intensity is equal to induced charge density divided by permittivity of free space. Let's substitute into this equation and so we're going to get, okay? So for induced, we're going to get the induced charge density, okay, induced charge density divided by permittivity of free space is going to equal, in this case, we're not going to have the initial charge density divided by permittivity of free space. So we're going to have initial charge density divided by permittivity of free space in brackets 1 minus 1 over epsilon R. These two cancels out, so it means the induced charge density is going to equal the initial charge density in brackets 1 minus 1 over relative permittivity. Let's call this equation 9. Now, there's one more to play with. We do know that charge density means charge over area, right? So if we substitute for charge over area, we're going to have induced charge divided by area of the plate equals initial charge divided by area of the plate. So if we put that, we'll notice that A tends to cancel out, right? So this is what we're going to have. We're going to have induced charge density to be equal to induced charge divided by area equals initial charge, okay, divided by area, and it's equal to 1 minus 1 over relative permittivity. A cancels A, because what we will notice is that the plate is not changing, the area of the plate is not changing. What we're only doing is we're putting a material in between, okay? So when A cancels out, we're going to be left with induced charge density equals initial charge into brackets 1 over relative permittivity. We're going to call this equation 10. So here are the 10 useful equations when you're dealing with dielectrics, okay? These 10 useful equations are very important in solving problems. So all you have to do is take note of these equations, go through the video again. If you did not get at first, you might want to play it again. And if you have a question, put it in the comment section, okay? Just put your questions in the comment section and I'll respond to it as soon as I can. Don't forget to click on the notification bell so that when a new video is being uploaded, you'll be one of the first few persons that gets notified. Now, what we'll notice about these last few equations, what we'll notice about them is in equation 9, equation 10, and then equation 8, 9, 10. There are some similarities. Notice we're just having E naught, we're having sigma naught, we're having Q and Q naught with the same values at the right hand side. So we're having some similarities between these equations. Okay, now it is important to take note of that relative permittivity is always greater than 1. okay, except the medium is air. Now, relative permittivity is always greater than 1. Hence, what we notice is that the initial value is always greater than the induced value. What I'm trying to say is that because relative permittivity is greater than 1, okay, so I'm going to come here to write something like that. Because ER is always greater than 1, it means Q naught has to be greater than the induced charge, okay? Epsilon E naught has to be greater than the induced electric field, and then as well, sigma naught has to be greater than the induced electric field. Okay, so it's important to take note of these ones as well. Okay, they could be possible examination questions. Okay, so in our next video, we'll be solving a problem on dielectrics. Okay, still on the playlist. Okay, do want to check it. Okay, to see how some of these formulas are being used to tackle problems concerning dielectrics. So do want to like, share with your friends. Okay, and as well, don't forget to subscribe to the YouTube channel so that you can as well click on the notification bell and get more info that will help you in your exams. Okay, so see you in the next video. Stay tuned.